Okay, so another classic tool for being able to assess the general value of one of these predictors is referred to as the so-called ROC curve. Stands for receiver operator characteristic, and comes from operations research during I think World War II. But the basic idea here is that we're trying to generalize the whole idea of a scoring function not at one particular cutoff, but at all possible choices of cutoff value. So the idea here is that if you've got some kind of scoring function, right, that you have an experimental observation and it gives you a score that basically is predicting, is this a positive test result or is this a negative test result? Clearly, when you cut at a particular value on that continuous scoring function, you are going to try to separate out positives from negatives, but typically, no matter where you cut, you won't get a perfect separation of positives and negatives, right? And as you move your cutoff up and down on the scoring function, you're going to be changing the mix of positives versus negatives that are above your threshold, right? So we can talk about that separation at a particular point of particular value of the scoring function, or we can look at the scoring function as a whole and ask, in general, how well does it work as a separator of true positives versus true negatives. So the basic idea then is that we are creating a curve that has two axes. One on the x-axis, we're basically showing our, let's see, we've got our true positive rate and our false positive rate. And ideally what we would like is to get all of our true positives without allowing any false positives in, okay? So imagine on our y-axis is basically our true positive rate, and on our x-axis is our false positive rate, okay? So if we choose a particular value of our cutoff, we're going to get some particular fraction of the set of true positives, but we're also going to get some fraction of what should be negatives are also going to score above the threshold. So what would happen if our scoring function was just completely worthless? It had no predictive value whatsoever. So it's basically, you know, just randomly picking things out of your data set. So then what would happen is your true positive performance would not be any better than your false positive performance. In other words, the probability of it giving a positive test result under the case where it really should be positive, in other words, H plus, is just going to be exactly the same as probability of getting the positive test result T plus given a case that should not be positive, in other words, H minus, okay? And that shows up on this ROC curve then as just a diagonal line y equals x going from 0 to 1, okay? Now, what if our predictor were perfect? Well, basically, it would rapidly pick up the true positives without letting in any false positives, and it would go all the way to picking up 100% of the true positives without letting in any false positives. So that would be equal to just climbing straight from 0, 0 to 0, 1. In other words, we're up here at the upper left-hand corner of our diagram, and then as we weaken the threshold, we'll gradually start to let in some false positives, but we've already gotten all the true positives. So here's an example of what this looks like with the false positive rate on the x-axis and the true positive rate along the y-axis. A perfect predictor would basically just start straight here and go right up to the top, and then as you weaken its criterion, it starts to let in more false positives until you reduce the threshold down to the minimum possible value and everything passes, right? So that diagonal dashed line represents worthless predictions, just completely random, and you can see what some real-world prediction methods, they basically do somewhat better than random, but not, anywhere near kind of perfect cutoff that a perfect predictor would obtain. Okay, so another measure that people use on these ROC curves as a general measure of predictor discrimination is what's called the area under the curve, which is basically just integrating the area under the curve. So you can see that a purely random predictor with no predictive value would have an area under the curve of 0.5, just be that triangle, whereas an area under the curve of 1 would represent basically a perfect predictor that basically separates true positives from false positives perfectly. Question?
I guess this depends on the application, but for example, if I want to have a predictor that is not going to have more than 10% false positive rate, then all I care about is the area until that 0.1 point, right?
Okay, so you're saying I only want to pick up, what did you say?
So I want to pick one of these tools to predict, and I cannot allow more than 0.1% false positive rate in my results. So the optimal choice here would be the black line.
Right, so you're basically drawing a line at a particular point on the x-axis, and you're asking which predictor gets me the most true positives at that point.
So is the best metric to use the actual number that corresponds to the 0.1, or is it the area under the curve from 0 up until 0.1?
So as I emphasized, there's a basic choice here between if you know a particular cutoff that for whatever reason is very important to you, and that's the dominant criterion, then you're talking about evaluating the accuracy at that specific threshold, right?
Yeah.
Whereas the ROC curve in general and this area under the curve metric is an overall measure of discrimination power for the total scoring function, not at any particular point on that curve.
Okay.
Other questions about the ROC curve? Okay.